Logistics-wise, for the exam, you get a cheat sheet. You can have whatever you want, one side of a sheet of paper. And you know the dimensions of a sheet of paper. I'm not planning on bringing in whatever size paper you want. The exams are usually 10 to 12 questions, and that's going to be about 2/3 calculation by points, 60-ish points are for calculation related questions just because they take more work to get the full credit. And 1/3 is conceptual multiple choice. And those will feel similar to the quiz questions. So if you were going to study for that, I would say the notes and the quizzes. The notes, because there are little things that I can't put a box around every single thing that is a takeaway. I usually reserve them for equations, just so you can see the end of a derivation. But there are things conceptually to know in between the lines, and those will appear when I do this recap. But look at the notes and then look back at your quizzes to prepare for the conceptual questions. For the calculation, that practice question packet is the best thing, because the questions are going to be pretty cut and dry, like your goal is to do this one thing, to calculate this one thing. And homework questions sometimes obscure that a little bit. So it's good to look back at those just for the sake of making sure you remember what the chapters were over. But for practicing, I think it's good to just continue working through that practice packet, also because it's brand new questions. So you get more experience rather than just looking over what you've already done. And there is one bonus question. It can be pretty much whatever I want because it's a bonus. So sometimes they're easier, sometimes they're harder. There is no requirement on my part of what it will be because it's extra.
About the cheat sheet dimensions,
yeah.
Like, what if the paper is like slightly bigger? Like a regular notebook's like 8 by 10.5, but mine is like 9 by 11 paper that I like.
Like 8.5 by 11 is what I consider standard. You said 9 by 11?
Yeah.
That's fine. It's more space than you need, in my opinion. So I've had people use 1/3 of the entire sheet. So I'm not that concerned about dimensions. It's just I don't want to see a poster board walking into this exam. I will give some advice on the cheat sheet, because what I see a lot of times is that you try and cram as many examples as you can onto the sheet, sometimes directly from my solutions for the practice. I've seen where people just copied and pasted them into a document, scaled it down, and then printed that out, which I am fine with. That's not the issue. It's that I don't think it helps that much. What I think helps is not a specific example necessarily, but what is the structure for the long questions, which for this exam, the long questions are the one where you have to find the flux through a box and then use that to find the charge inside it with Gauss's law. The one where you find the net electric field. And actually, I'd say that's pretty much the two big long questions that you do for these chapters. And if you only have one specific example, it'll help you do that example if that's what I give on the exam, but what are the chances of that? Instead, if you just tell yourself how you solve any question about finding a net electric field, you will be in a lot better position. And it also helps you not freeze up when it's not exactly the same as what is on your paper. So for electric fields, for example, just so you can see what I mean by like, what is the structure? I would just have a step-by-step, what do you do? And you can make that as detailed or not detailed as you want, whatever you need. But for me, this would be like draw vectors for each of the individual fields, and how you determine the direction of those vectors is which way a positive charge would be pushed. And so if you've got a group of charges, then if this one's positive, this is negative, then a little positive charge at this dot in the middle would be pushed away from this charge. I'll call it charge 1. So that's the direction of the field of charge 1. Here's charge 2. And I'm not necessarily going to try very hard to make this neat because I'm giving an example here. But E2 and then E3 is towards it because charge 3 would attract a little positive charge at the center. And then E4 is this way. But notice I'm anchoring all of the electric field vectors to that dot. If you don't do that, you can get confused about how to add those vectors. And that is really the next step, is once you've drawn those in, these remaining steps are essentially vector addition, but you could make that into like find components of your electric fields, find the net electric field from those components. And I mean, like symbolically at this stage, you'll have something like E1 cosine whatever plus E2 sine something. So it would look like E1 cosine whatever plus E2 sine whatever. And with that, you're going to need, in order to get values, use that the electric field strength is K times the size of the charge over the square of the distance. And then that the overall net electric field is yada, 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 all the Pythagorean theorem and your usual vector addition stuff. All right, so that's the first thing, is for those really long questions, it's easy to forget certain steps unless you have a step-by-step guide written out for you. And then you could include one example if you can squeeze it in just to show this being applied, but I wouldn't do more than that with it. Another thing that's good to have on a cheat sheet is the variables, so a list of variables. Because I'm going to give you the equations. The equation sheet is the one that's in the review packet. But you have to know what those equations are saying in order to be able to apply them. And to know what they're saying, you got to know what each symbol represents. So I would say you'd have 3 columns: the quantity, the variable, so the symbol for it, and then the units. And again, go as far into this as you would like, because there are quite a few things we've defined. Which of them is like, you know it and you don't need to write it to know it, it depends on you. But things like that the electric force, we use F. And it has units of newtons, which you could write that out or just use the symbol. It's up to you. Fields, we use letter E for, and the units are newtons per coulomb. And you could keep going with this. Once you do this, you can sort of translate the equations in the equation sheet into statements. And that's because that's the point of math in physics. It's to condense down long statements into very precise shorthand. That's what an equation is to a physicist, is a shorthand of a more verbose English description of something. I'd say those are the main 2 things. Past that, it's whatever you would like to put on there. You could, if there are certain equations that trip you up, you could do like we've done in class. So if you're confused on what this one's saying, do the labeling to say this is the field of charge Q. This is how big the charge is. And this is how far you are from it. Whereas K is just a number. We call it Coulomb's constant, but it is just a number. This will be the big picture of what we've done. This will be the big picture of what we've done from chapter 21 through 23. And it's essentially adding layers. So the first thing we ever learned about, and this is historically and in the course, is charge. So all the things about charge, meaning how things become charged, that there's positive and negative, that negative charges are what move. That one actually did take a lot longer historically to figure out that it's the electrons moving around, but anyway, it goes with the charge. The next layer is forces between charges. So that like charges repel, unlike charges attract, and more specifically, Coulomb's law. It says how big that force is if you're talking about 2 point charges, 2 globs of charge. But then we asked the question of how can that force come about if those charges are far apart from each other? Electrical forces are strange like that. Gravitational forces are strange like that, where things don't need to be touching for them to occur. So we said, well, maybe they are touching in some sense. It's just touching something we can't see. Maybe each charge makes something invisible around it, and the other charge is touching that. And that's how the force comes about. Rise from electric fields. So that's our letter E. And this one is going to take quite a few things, so I'll maybe just separate it like that. The first is that the size of that force is equal to however big the charge you're putting into the field is times how strong the field is. So if we have one big charged thing and we put one little charged thing in its electric field, the force the little thing feels depends on how strong the field of the big thing is at that location. This is the size of the little charge. This is the field of the big charge. And so then we sort of shift perspectives. Force is not really the important thing, it's the field itself that the force comes about from. And so now we look at the properties of the electric field. And that'll be that its direction is the direction of the force on a positive charge. And the force that comes about when you put a charge into this field depends on what kind of charge you're putting in it. So positive charge follows the field, meaning forces along the electric field direction. Negative charge goes opposite the field. And that's if you're putting them into the field. So this is the role for our little Q0, the one that's sitting in the field of the big charge. If we're talking about the big charge, so the properties for it, the field points away from positive charge and toward negative charge. So I'll sketch that over here. It's the same scenario I was just looking at, but I'll look at 4 possibilities. So let's say Q is a positive charge, Q0 is also positive, then Q is negative, and then Q0 is still positive. Then Q is positive again, while Q0 is negative, and then both are negative. In that case, I start by looking at Q, the one making the field. This side makes the electric field, this side sits in it. Positive charges make fields that point away from themselves. So the field due to charge Q points away from it at every location in space, including at where Q0 is sitting. Since Q0 is positive, it feels a force in that direction. All right, for the next one, charge Q is negative. It makes a field that points towards it. So I'll try and keep this part of the color code the same. Points towards it. But charge Q0 is a positive charge, so again, it follows the field. In case 3, charge Q is positive. It makes a field that points away from it. But charge Q0 is negative, so it goes opposite that field. And then in case 4, charge Q is negative, so it makes a field that points towards it. Charge Q0, which is sitting in that field, is a negative charge, and so it moves opposite the direction of the field. And that's our new explanation of attraction and repulsion. It's how one charge creates a field and then how the other responds to it. If you're stuck there thinking, why is it that one charge makes it and the other just sits in it? What makes the one charge more special than the other? And the answer is nothing. If you're talking about two charges, both are playing both roles. One of them is making a field, but it's also sitting in the other charge's field. And the fact that both get closer to or further apart from each other is a result of both sides of that interaction. Each one sits in the other's field. So that's what fields are. And the rest of chapter 22 is essentially just figuring out what they look like for different objects. That's not really a new layer. That's just what does E look like depending on whether you've got a disk or a dipole or a ring or what. The real next layer is you go from the idea of individual field vectors to field lines. So this is continuing from where we were. And that starts to show you the shape of the electric field. Instead of drawing this field at particular points, saying, okay, yes, charge Q makes a field that points away from it right here. It also makes a field that points away from it over here and then over here, because if I put a positive charge at any of those locations, they would be pushed away from charge Q. I get tired of doing that and worrying about every point, so I say, well, generally, charges will be pushed along that line if they're over there, or this line if they're over here, and so on and so forth. And a few more. But now that's showing us what the field looks like around this charge. And this is actually a big step because we've moved from back here, it was mysterious why forces happened between charges that were separated from each other. Now we've drawn the invisible thing surrounding the charge. I know why if I put another charge Q0 over here, it starts to move away because it's touching the field itself. It's not touching the charge, but it is sitting in its electric field, and that's where the interaction is actually happening. Okay, so field lines make the invisible visible. And what we can do from there is, for one, just say, well, here's a rough guess of which way charges get pushed around any charged object. They will generally be away from positive charge and toward negative. But they also reflect how strong the field is. So here, we've got a stronger field than out here because the lines are closer together. That's not the physical reason, but you can just read it off the picture. From there, the next layer is Gauss's law. But it's really just a statement that says, man, I've drawn a lot of these pictures. I know what the electric field looks like for lots of different shapes. I start to notice a pattern. And the pattern is the field lines actually tell me quite a bit about what kind of charge it is I'm dealing with, both in their shape, but also in how they flow. I imagine them as water spraying out or water sinking in. So this is where it's especially good to think of positive charge as a water fountain or a fire hydrant, and negative charge as a drain or a sink, just whatever gets the visual across to you. And what Gauss's law says is that just knowing some information about the field tells you about the charge. We use the idea of a bag enclosing the charge to think about this, but it's not really the bag that's the important bit. It just is our device to tie the field to the charge. So Gauss's law says number of lines poking through what charge is inside the bag. And all we had to do with that is turn it into a formal statement, meaning one we can actually compute with. So that's what this flux interval does for it. It is how we count field lines. And it does tell us about what charge is inside the bag, the enclosed charge. So I can ask conceptual questions about this, and that's honestly harder than the really long calculate the flux through a box type question, because that has an algorithm to it. It's the same every time. The conceptual questions for Gauss's law are hard because they really are just, what does Gauss's law say? And does your answer agree with what Gauss's law has to say about this situation? All right, so that's sort of how we've built up through the chapters. That's the through line. Now I'm going to just try and say like, okay, but what should I study? So I wanted you to see the big picture. But what should I study for chapter 21? Types of charging, meaning conduction, induction, and friction. And Coulomb's law. Can you calculate the size of these forces between two charges? Can you tell me about the direction? Can you do that if we've got three charges present? They won't be at weird angles. I'll save that for electric fields. But just can you figure out the direction of the net electric force? So find the net force on some charge. And the last thing, which I don't really think of as a separate thing, but it's just people forget it a lot, it seems like, on exams. The total charge on something is always a multiple of the electron charge. So if I state something in terms of how many electrons it is, you can always multiply that number by the charge of an electron, 1.6 times 10 to the negative 19, and that will give you the total charge. Or if I give you the total charge and ask you how many electrons it is, you divide the total charge by the electron charge. Okay, so it's an equation in a sense, but it's really just a common sense statement of a pile of electrons is equal to the charge of a pile of electrons. 22, what fields charges make and how they respond to fields. So when I say what fields they make, I mean what is the direction of the field based on if it's a positive or negative charge making it, and then the size of the field, which depends on what shape the object has. If it's a point charge, it has a formula for it. If it's a capacitor, it has a formula for it. But those are just, it just depends on the thing that's making the field. And then how they respond to it, again, the direction. So what does a positive charge do in an electric field? What does a negative charge do? And again, the size of this, but this one's easy because we've only talked about putting point charges in a field, more or less. It's always size of the charge you're putting in the field times the strength of the field, which just brings you back to how do you find the size of that field. And more specifically for calculation, finding a net electric field, which there's a step-by-step on how to do that in the notes, and also that's sort of what we were going over for the cheat sheet. You don't have to derive anything. There will not be calculus on the exam. So I'm not expecting you to be able to tell me how you get the field of a disk. That was my job. You just have to be able to use that information to say, well, at this point near the disk, a little charge feels a force this direction and of this size. And for chapter 23, what does Gauss's law say? Those are those questions in the homeworks and practice and all that where it feels like it's hard as a conceptual question, but then if you actually use Gauss's law, it gives you the answer immediately. It says you're thinking too hard about this. The answer is just this. For instance, things like here's our charge, here's that same charge one more time. We're looking at three scenarios. And the first is, what's the flux through a Gaussian surface of that size? Versus in the second scenario, what's the flux through a Gaussian surface of that size? And in the third scenario, the charge is surrounded by a metal shell, a neutral shell. And the question is, what's the flux through that Gaussian surface? And you start to think, well, I don't know, it depends sort of on the field lines. And nope, Gauss's law says it just depends on what the charge is inside of that bag. It's the same charge inside of each, so the flux through all of them is the same automatically. Takes no thought according to Gauss's law. So questions like that, don't think too hard. And then for population, it's the flux through a cube. So I guess I lied a little bit. This is where the calculus shows up and finding what charge is inside of it. But it would be very much like that example that's in the notes and the ones you had to do in the homework and the ones that are in the practice. Well, this is kind of my bit. I did get some questions over email, so I'll start with those, but pretty soon here it's going to be up to you what you want to discuss. So, any questions? Does the electric field of an object always mimic the object's shape, meaning sort of conform to it? And in a sense, yes. More or less, the answer is yes. And it's because we found that, that reminds me of one little thing here, properties of conductors, because that's more conceptual, just what things are true about conductors in general, which was one of the last pages in that chapter. But this is generally true for conductors because the electric field has to be perpendicular to their surface. So if you've got a sphere of charge, a metal sphere, the field lines have got to point perpendicular to its surface, and that means they sort of reflect the shape in the same way that if it were a triangle, that would force the field lines to point in a different way. And they bunch up a little bit at the corners because some charge tends to congregate, or more charge congregates at the corners. So yes to that question. The next one was, does force always oppose the direction of the electric field? The answer is no. Only if the charge sitting in this electric field is negative. So whether I've got a positive or a negative charge making the electric field, so for a positive charge it points away, for a negative charge it points towards it, the direction of the force depends on what I put into that field. If I put a little negative charge into this field, it will feel a force opposite the direction of the field. If the little q0 is positive, then the force will be in the same direction as the electric field, partly because that's how we came up with the direction of the electric field in the first place. How do you measure an invisible thing? You hold something up and see what happens to it. And we just by convention decided a long time ago that we will always hold up a positive charge and see what happens. Because if we didn't, we'd get a different answer depending on whether we held up a positive or a negative charge. And that's not a consequence of the thing that's making the field. That's a consequence of the thing I am putting into it to test it, which means that I'm not saying or making a statement about the electric field itself. when I say the answer is different for a positive versus negative charge for this one. All right, so we had to pick. So we had a consistent definition for the electric field. Does the electric field of a positive charge spew outwards like a fountain, and the field of a negative charge is always towards the charge, so like a drain? Yes. I won't write that one down, but yes. Will there be integrals that need to be calculated? The answer is only that flux one, the amount of flux through each face of a cube, and I even showed you a shortcut way where you didn't have to do those integrals. It's only like that for something with flat surfaces, but you're allowed to do that if I told you you could do it that way. What type of assignments most closely mimic the exam? The practice question packet that I put up in the exam one module, and then quizzes for conceptual. How many questions? I covered that one. And the last one was, how are you today? Which is very nice, thank you. I'm not doing very nice necessarily, but that is very nice of you to ask.
I have a question.
Yeah.
Can you go over number 9 on the practice exam? So I was like looking through the solutions. I was trying to figure out how did you get 311.6 newtons.
311. Let me check my math. Yeah, that's what I get when I put those numbers in. So are you asking how I got these numbers?
Yeah, so like is that number from F2 on 1?
Yeah, so
Oh.
Q1 and Q2 are the 15 microcoulomb, that's what this is. The 13 microcoulomb, that's what this is. And the distance between them is 0.075.
Okay.
Yep. Okay, and again, this was where I was saying, like, this is maybe overkill to ask for forces because I'll ask a similar question about electric fields, and it's a very similar process. So if I were to ask about net electric force, I'd probably stick to a question closer to this one because I'm going to save like 2D vector addition stuff for electric field questions.
I had a question about the conceptual part of number 12.
Okay.
I didn't really like understand of like how the direction was to the right. I didn't really like understand that question.
All right, well, let me start with just two charges. So say I've got a positive charge up here and a positive charge down here. What would the direction of the electric field due to this charge be at this location in space? So that's not a zero, that's like a little ball of charge.
Would it like repel?
Yeah, it points away. Repel is, it makes more sense if there literally is a charge here that's being pushed, and we can use that idea to think about the electric field, but the electric field is made by this, it points away from it. Does that distinction make sense?
Yes.
Okay. So I'll call that E1. What about the field from this one? Which way does it point at this location in space? If you're not sure, you imagine pulling a little positive charge out of your pocket, holding it up at that point, and seeing what this charge does to it. What would it do to it?
It's gonna also repel.
So this field is also away from that charge. If I add those two vectors, what do I get out the other side? Which way will the resultant vector point?
Oh, I see. It's gonna go to the right.
Yeah,
Right.
and all that's happening in the ring is that same process many times over.
So it's kind of like the parallelogram law in statics.
Yeah, so I mean, you can add these with parallelogram rule because it's the rule of vectors. That's just how they add. So the net of those two would point to the right. But that's kind of what I'm getting at here is I can pair off charges making up this ring, top and bottom. So I can 3 and 4 are a pair, and I find that their net electric field points to the right. 5 and 6 are a pair. Their net electric field points to the right. 7 and 8 are a pair. Their net electric field points to the right. I'm adding many things who each of them has an electric field that points to the right. Does that answer the question?
Yes.
Okay. Other questions?
I know I have like a lot of questions.
No, that's good. You're helping me.
Could you also review the number 11 where you had like the directional charges?
Sure. So I'll start fresh on this one because it's easier to talk through that way. So these are points in space, whereas P1 and P2 are actual charges. And the question is the direction of the electric field at each of these points in space. So I have to go through this process of finding the net electric field at each location. So at point 1, does the electric field of P1 point away from P1 or towards P1? So does this thing's electric field point away from it or towards it?
I think away.
Away. And if you're not sure, you imagine pulling a little positive charge out of your pocket, holding it up right there and seeing what happens to it. It gets pushed away. So that is the direction of the electric field. This is like when the wind is blowing and you want to know which way it's blowing. What do?
Uh, would they like hold up their hand?
Yeah, people they lick their finger and then hold it up, and it's just because they can feel it cooling their finger. So that gives a rough sense of which way the wind is blowing from on your finger. Your finger is just a tool to test. The thing you're testing is the wind, but the wind is invisible. So that's the best you've got to test it, is hold something up and see what happens to it. Very similar idea here. The field is the important thing. It exists of this charge, but the only way you're going to see it is by holding up a little positive charge and seeing what happens to it. That's the finger, or that's dropping a leaf in a river to see which way the river flows. Okay, but that's why I make the distinction of away is better terminology here than repels, because that's just a number describing this charge. It's not anything about a force. Forces are just how we end up being able to see what the field looks like. Okay, so that's a long-winded thing, but that's E1. What about from charge 2? Which way does its field point at location 1?
Will P2 point away from P1?
The field of P2 will point away from it. P2 is also a charge. The electric field of positive charges points away from them in all directions. So those are my two individual fields. Which way does the net electric field point at location 1? If I add those two vectors together, which way does the overall vector point?
To the left.
Yeah. All right, at point 2, location 2 in space, which way does the field of charge 1 point?
Is it to the left?
So what kind of charge is charge 1?
Positive?
Positive. And our really only way of testing what the field looks like is I pull a little positive charge out of my pocket while I'm standing at location 2 and see what happens to it. What would it do?
Repel?
Repel. So it'll that little positive charge this way. This is what the field of charge 1 looks like there. That's the direction the wind is blowing right there.
I have a question.
Yeah.
How come you said it's pointing to the right, correct?
Yes.
How is it that the answer is E though?
Because we've only considered one charge so far.
Okay. Got you.
All right, so now we are going to look at charge 2 and what its electric field looks like at that location in space. So charge 2, what kind of field does it create at that location 2? Which way does it point?
Will it also be to the right?
So charge 2 is a positive charge. If I held up a little positive charge right here, what would charge 2 do to it?
It's gonna repel. So it'll go to the left.
And so it's tempting to say that the answer for location 2 is 0 because these point in opposite directions. And this is where my picture fails a little bit. What I'm noticing in the original picture is that point 2 is closer to charge 2. And that's going to mean electric field 2 is actually stronger right here. In other words, it wins that battle between E1 and E2, and that's why the net field points to the left. This would be like you've got two fans blowing. You face them towards each other. Which one wins? The stronger fan. At location 3, which way does the field of charge 1 point?
To the right?
To the right. That's the direction the wind from charge 1 is blowing. Right? What about from charge 2?
Also to the right?
Mm-hmm. And since they're both in the same direction, I don't have to worry about their relative strengths, but which of those two fields actually would be stronger?
Could you repeat that again?
Yeah, I'm asking which of these two fields is stronger at location 3?
Would it be the first one, E1?
What makes you say so?
I guess like from the line, like E2 is a little bit longer. So like I think like the farther you are from the field, like the farther you are, the weaker the field is, but the closer you are, the stronger the
I
field
agree,
is.
but which charge is this point closest to? Is it closer to charge 1 or charge 2?
Charge 2.
Charge 2. So electric field 2 is actually the stronger one. It's actually significantly stronger than field 1. But the net field overall still points to the right. A question like this, if it's not automatic for you, of like for positive charges, field points away, for negative charges, it points towards, these will be very hard questions. So I would suggest practice this one a lot. Really understand why my answer is what it is, meaning why the diagram is the way I've drawn it. Other questions?
For number 15, was it mostly like plug and chug for number 15?
It is if you can do that first step that we were just talking about of
Okay.
location in space, which way does each field point? That's actually the hardest step and the one that is wrong the most on these exams, because everyone thinks that's the easy step and then they draw it in the most wild way I've ever seen sometimes. So I would say be very sure that you can do step 1 of finding the net electric field. And then I don't think the vector addition stuff is really the struggle that most people have. It's just step 1, which is which way does each field point at that location in space. It's sort of a thing of like everyone thinks they can fight until they get into one.
Could you go over question 21, please?
Okay, so an electron is shot from plate A to plate B, hits plate B with a speed of 700. What is the magnitude of the field between the plates? I will be honest and say this one is sort of a stretch problem, and I try to order these sort of from easier to harder by topic, so it gets hard for the topic of finding electric fields, and then it ramps off, and so on and so forth. So this is a harder question, just to get that out of the way. But how I would think about it is they're telling me about the motion of the electron. So they're telling me that it zips towards the right and gains this much speed. That is then going to tell me about the acceleration of the electron. I know what it was going at initially, and then its final. It's kind of hinting at an acceleration happened. But acceleration depends on the net force on that electron. That's Newton's second law. And then I ask, well, where is that force coming from? Oh, it's the electric force coming from this electric field made by the plates. And so if I can kind of work backwards through all of that information, get from velocities to acceleration, acceleration to net force, and then net force to the electric field that causes it to happen, then I can find the electric field strength. And that's sort of what I'm doing as I go through this. Is that the question, or is it something else?
Yeah.
Okay. This probably wouldn't show up on the exam as a question like this because I don't necessarily like to mix Physics 1 in on exams, but it is still valid. It is still relevant. And in a real life sense, you got to use both. You got to be able to reason about both just general motion of stuff and specifically about electricity. And Newton's laws still work for it. Other questions?
I had a question not regarding about the exam, but more of the homework. About finding the magnitude of the initial acceleration.
Mm-hmm.
How do how do we go about that?
Could you read me like a snippet of the question?
Yeah.
Okay.
Um. Okay, so it says an electron is released 9.6 centimeters from a very long non-conducting rod with a uniform 7.9 mu coulomb over meters. And then it says, what is the magnitude of the electron's initial acceleration?
Oh, okay. So an electron is released right here, and they've told me about the charge density. That's what the coulombs per meter is how dense the charge is packed onto this rod. And they give me the distance I am away from it, right? That was a given number.
Yes.
Okay. So this is actually sort of similar to the capacitor thing. It's asking about an acceleration, but what determines acceleration?
QE over M.
Well, yes,
Just
but
bring it.
even more directly, the net force is what determines the acceleration of anything. Like that's what the second law is getting at is just because these are charges doesn't mean they break those laws. Okay, technically they do at the quantum scale, but for us in the classical world and for large amounts of charge, this is okay. And so what I'm saying here is by knowing acceleration, I have a path to finding net force. But by knowing net force, I have a path to finding the electric field because that's where the force comes from. That's what makes it happen. And then it's really just a question of how are they related? Acceleration is net force over mass, and then the field is the size of the force over the size of the charge sitting in it. So I can just combine those and say electric field is the force over the charge, specifically the electric force, but that's the only force present here. And so it is the net force. So that is mass times acceleration over Q0. And so acceleration, if I solve for it, is that right there. That was a little bit roundabout. I could have done that better. I could have said force is QE and put that directly in right here. That's probably a more straightforward way to do it. But
Okay, because the way
yeah.
that I was working it out, it was different because I was doing the charge divided by the distance of the I think it was the electron. Hold on.
It may have been that you were thinking about, so this is still something that we would have to sort of pull out of this problem because it is specifically the electric field of a charged rod. That's what's causing this acceleration to happen. And that has its own expression. It's charge density over 2 pi epsilon 0 r. Is that what you were talking about?
Yes.
Okay, yeah, so you're not wrong. That just determines one part of this acceleration.
Oh, okay.
Yeah. Okay, does that clear it up?
I have a question.
Yeah.
So it's not exactly about the exam. I mean, I guess it's the graded practice for chapter 23, which is kind of part of the exam. But I had a question about number 4 on it, which I mean number 9, which was the one about the Gaussian surface.
Okay.
And basically it was So the question that tells us to like use the slider to move the point x equals r divided by 2, I didn't understand how we got the answer by that. Like, could you explain it a little more?
Yes, give me a minute to pull that up because I think that's going to be easier if I'm directly looking at it. It says move this to half the radius, and that would be like that-ish, right?
When I did that, I didn't understand how the answer would have been that the flux was 1.3 e to the 5 because it shows that it shows that it's 0 at the top, so I didn't understand how it would still be that as the answer.
That's a good question. All right, it's a 0, so we move it to... Oh, we're both reading this wrong. We're reading this as diameter over 2. It's radius over 2. So half the radius is actually to about like here. You see what I'm saying?
Oh,
So it
okay.
still
I think
contains the charge, and so the flux is still equal to that charge over epsilon 0. But you are correct. If it were diameter over 2, so the radius, then it would not enclose the charge anymore, and so the flux should be 0.
okay. Thank you. I think I get it.
Okay. Yeah. I mean, I just did the same thing. So that's a very reasonable, I guess, if I'm the basis for what's reasonable.
Yeah, I have a question.
Yeah.
Um, so from chapter 22,
Mhm.
to find the net electric field, right?
Yep.
What would be are there any like steps that I could follow, like step by step? Like would I need to like find the electric field of like the charges first, and then I'm not sure what to do.
Let me pull up the notes. So in the chapter 22 notes, it is page 4. So these are your steps in the box.
Okay, thank you.
Other questions?
I had a question again regarding about the homework for problem 15.
Okay. For chapter 23 homework?
Yeah, yes. Like, how would we start off the equation? Well, the first step into solving this problem.
Okay, so this is one where because we got a little bit behind on Gauss's law, um, this is that last example that we're going to do is what will really clear this up. So we will cover it in full before then, but I'll kind of walk you through it now. So what is the charge on the cavity surface? So it's talking about this inner surface. And the easy answer to that is, first of all, what's the electric field inside of a conductor? That is a property of conductors we've discussed.
Is 0?
Is 0. So the electrons will move around until they've gone back to this 0 electric field, because that's what's going to make them stop moving. They shift until that happens. And once it does, it stays at 0. So within this metal, and that's what each of these are, is it's supposed to be metal, the electric field is 0. All right, next part is imagine a Gaussian surface, a bag that's embedded in the metal. If the electric field is 0 inside of the metal, how much flux is there through that bag? How many field lines pass through it?
None.
None. Okay, what does Gauss's law have to say about what kind of charge is inside that bag then? If you see no field lines passing through the bag, what kind of charge is inside the bag?
No charge?
No charge. All right, so for cases 1 and 2, you're done because that's the only place charge could be, is on that inner surface. There's no charge within the cavity, So it's got to be on the inner surface if your Gaussian surface is embedded in the metal, because charge always moves to the surface for conductors. So that's why the answer is 0 for these first two. Does that make sense?
Yes, and for 3 and 4, we'll be using the lowercase q, which is the -1.
Almost. You'll notice it's +1 right here. That's the answer, even though that lowercase q is -1. Why would that be?
Wait, you said it's positive where?
In the answers, these are the answers right here.
Oh,
So why is it that the answer
it's
is
positive.
+1, even though it says it's a -1 charge inside of the cavity?
Would it be to cancel out? Cancel out?
Yeah, so that the net charge inside of the bag is still 0. So,
Okay, yes.
yep. So I'm going to come over here and I'll just sketch all that out real fast, just so you can see the full argument. But that is the idea. So this is one of those places where Gauss's law feels like magic, because I see a circular hole within a square cutout, and I drop a little charge in the middle. And somehow just from that, I can tell you how much charge is on this inner surface. And in fact, I could even tell you how much is on the outer surface if I know how much net charge that metal has. So how I do it is, the first fact is 0 inside of metal. It's a conductor, so everywhere in it there is no electric field. The next fact is I can draw a Gaussian surface embedded in the metal. It's a bag. It is inside of a material, which is kind of weird to think about, but it's a mathematical bag. It's an imaginary bag, so we're allowed to do that. All right, Gauss's law says count up how many field lines pass through that bag, and it'll be able to tell you how much charge is inside of it. If there's no electric field, there's no field lines to poke through the bag. So that's my next fact, is the flux through that bag is 0. No field lines pass through. But Gauss's law says the flux through a bag is always equal to the charge inside of it over epsilon 0. So if there's no flux, there's no charge inside. But I look at this and say, but yeah, there is. It's right there. It's a -1 microcoulomb charge. And then I realize what actually must have happened is when I put that -1 microcoulomb charge inside of the cavity, it repelled the electrons in the metal away, leaving what kind of charge on that cavity surface. But that will leave positive charge on this inner surface. But there's my answer for how it can be 0 charge inside of this bag. Because it's not saying there is no charge, it's just saying that the charges add up to 0. I've got an equal amount of negative and positive. If this is -1 microcoulomb, there must be +1 on the surface, so that the net enclosed charge is 0. Gauss's law says it has to be.
Could you go over number 31 on the practice test?
Yes.
And like also, with those types of questions, did you say that we can only use the shortcut if it's only for a flat surface? Like, could you explain the process
Sure.
on like how to solve the problem?
So it's much easier to check your answers if you can sketch the vector field. And that is a skill that you don't formally learn about or develop until Calc 3. So it's not that you have to be able to do it. I'm not testing on it, but it will help you get the answers. So that's the first thing I do is I see here's the electric field, and what it's telling me is that it points in the z direction, the k-hat direction, and it gets bigger the larger z gets. That's what I've drawn, is vectors pointing in the z direction that get bigger the larger z is. Then what I'm writing here is me just answering, do lines poke in, poke out, or neither on each face? I'm not even thinking mathematically yet. I'm just literally using my eyes and saying, are they poking in, poking out, or neither? So on the right face, does it make sense why the flux is 0?
Yes.
Okay, and then so on and so forth. There's no lines through the bottom face. There's no lines through the left face. There's no lines through the top face. Lines are only going into the back face, which is why it's negative, and out of the front face, which is why it's positive. If my calculus answers are different than that, I did the calculus wrong because I've already used my eyes and they've told me what the answer should be. So now I go to the calculus and I say, how do I formally count how many lines poke through each face? I add up how many field lines poke through, that's the dot product, each little patch of that face. This is the electric field, that's what describes it at any point in space. And then, depending on which face I'm looking at, I have a different area vector that describes which way is the outward direction. So for the top face, outward is up. For the bottom face, outward is down. And that's what I put my unit vectors for, to say, for the top face, it's in the j hat direction, for the bottom face in the negative j hat, and so on and so forth. And then I have to evaluate these dot products. For that, this is usually how I write it, as just sort of like a mnemonic, is if you're taking a dot product between two unit vectors, it will be 1 if they're the same vector, it will be 0 if they're different vectors. And there is actually a name for that. It's called the Kronecker delta function, if you were ever interested, but don't worry about it if you're not. From there, I just evaluate these dot products, and that was real easy for these 4 because the vectors were in different directions, k hat versus I hat, or k hat versus j hat. It's hard where I've got a k hat and a k hat, and it's because those give a dot product of 1, and then I have to evaluate whatever's left. So what's left after I take that dot product is 5z squared and dA. So I have to do this integral. And then that's where I get a little desperate and I say, I really hope I'm not actually integrating in the sense of like integral of z squared dz. I hope that there's a shortcut. And for y'all, there always will be. I will not give you something where you have to do a quote unquote real integral, meaning z is actually the same number everywhere on that front face. It is always 5 on the front face, which means z is not a variable. It's just the number 5. And so I can pull it out of the integral as well. And so what I'm really integrating is just the area of that front face, all the little patches making it up, to get the overall area. That's what the 3 squared is. It's just what's the area of a square, length times width. And the shortcut there is just use an area vector that already describes the entire front face, for instance. You don't have to actually break it into little patches and add up because all the patches kind of look the same on that face. If it were a curved surface, different patches point in different directions. So dA is a different thing depending on where you look. And that's why you have to use calculus for curved surfaces. But the shortcut is just already call this, let's see, 5z squared and the k hat. If I'm talking about the front face, the entire front face, its whole area, points in the k hat direction. And so I really am just evaluating what is 5z squared. Well, on the front face, z is equal to 5. Oh, and I've lost my area. There it goes. On the front face, z is 5, and the area of the front face is 3 times 3, length times width. So that's how I get my number here. The last part is just one that you kind of do once you're done. And what I see happen a lot is, I think, just fatigue. People get to here and they say, I think I'm done. I've done a lot already. They forget the last step, which is add those fluxes to find how much points through the entire cube and use that to find how much charge is inside the cube. That's like the mystery you're solving for these questions, is what's inside the box. Other questions?
For like a charge in a field, will we be giving like what charge, like what type of charge it is, or do we always assume like, oh, it's a positive charge? I was just wondering because I feel like I was like very confused on questions asking about like, oh, what direction would the charge go? But like I didn't know what type of charge it was.
Gotcha. Okay, meaning like whether it was positive or negative?
Yeah.
Okay. I think I would be clear about what kinds of charge you're dealing with, both for the thing making the field and what's sitting in it. If I weren't, it would be because you observe in the problem that something's moving opposite a field, and so you have to infer from that that it was a negative charge moving in the field. Does that make sense?
Yeah, that makes sense. I
Okay.
was just confused because I feel like for some of the like practice problems, maybe I didn't understand like the word
If you
or
could give me a
something.
specific problem, I'll try and clarify.
Okay, I don't have a specific problem right now, but I get it.
Maybe be looking for one because we'll come back to that if there's other questions in the meantime. Okay, this is another good one just to point out. This is a what does Gauss's law say type question. So I'll go through these just to clarify the differences between field and flux and then why this is, even though it may not seem like it, an easy question. So we imagine bags around this charge, three different size bags. And it's asking me first, how strong is the electric field through each bag? And for that, I just have to remember features of electric fields. They get weaker if you get far away from something that makes the field. Charged objects have a weaker influence on the space around them the further away you get from them. So that's why I said rank from closer to further away for the electric field strength. That's just, if you want to think in terms of field lines, that they spread out as you get far away from the charge. The harder question is how much flux there is through each sphere, or at least it seems harder at first, because flux, if you're thinking math-wise, is this integral, and you start worrying, well, I don't know, because this is different for those different spheres. I just said that in number 28. And then the area of each sphere is different. So is this different too? Turns out those two things exactly cancel each other out. Yes, the field gets weaker farther away, but the area gets bigger. So when you multiply them, that stays the same. That's one way to see that the answer is the flux is equal. Another way to see it is because Gauss's law says so. All three of those bags enclose the exact same charge. And so all three of those bags have to have the same number of field lines poking through them. Gauss's law says so. A third way is looking at the lines. So remember, there's sort of the spirit of Gauss's law. That's what's on the first page of the chapter 23 notes. And then there's the mathematical statement of it. They should agree. The spiritual version is just count how many field lines poke out of those bags. It's the same number of field lines no matter which bag you look at. So that kind of is the same as answering with Gauss's law, but just a more loosey-goosey way. Right? Any luck on that question?
Oh yeah.
Okay.
It's on the practice questions
Mhm.
in Wiley, chapter 22.
Gotcha. So this is that thing which I think it's a hard thing to communicate, but let's imagine like wiping the slate clean and we know nothing about electricity, okay? So that's where we have to start this from is just imagine you are the person who is studying electricity back in the 1700s. Well, you're studying something where every charged object, it definitely does something to the space around it. Like I imagine like the Van de Graaff generator, the big charged ball thing that we have in class. If I hold up a little charged object to it while there's no charge on the Van de Graaff generator, nothing interesting happens. And yet suddenly, when this Van de Graaff becomes charged, it could be positive, could be negative, the little charge I'm holding either zips towards it if it's a negative charge, or it shoots away from it if it's a positive charge. And so I say, interesting. Why does that happen if they're so far apart from each other? I'm used to forces being things touching. And so that's where I invent the idea of the electric field. I say there must be something around the Van de Graaff generator that I can't see. And my little charge is in that. And so I say, well, that thing, depending on what I'm holding, either pulls it in or pushes it away. But that's just because I'm holding two different things and seeing what happened to them. The thing making this invisible field is not changing between those two experiments. And so if I want to talk about it rather than what I'm holding up to it, I've got to come up with a way to define a direction for it. And that thing should be the same direction whether I hold a positive charge up to it or a negative charge. The problem is if I try and define it in terms of what the charges do, I do get two different answers, depending on whether I held up a positive or negative charge. And that's not going to work for me. I can't say that this electric field points both ways. I have to pick a definite direction for it. And that means I just need to come up with, I like positive charges better. So I'm going to say from here on out, what this charge does is, which I just realized I have those backwards. The negative should repel and the positive should attract. Hopefully that doesn't mess everything up. But what I'm going to do is just say from here on and forever, I'm going to say this invisible field points in the direction the positive charge goes when I hold it up. And that's why we say test charges are positive. It's a statement that we have to make to come up with a consistent direction for electric fields, period. Does that make sense?
Yeah.
Okay.
Kind of.
So this is a long-winded way of saying, like, we picked at some point in history, we decided that the electric field points in the way a positive charge moves when you hold it up near the charged object. We could have, way back in history, decided that it's the direction the negative charge moves. And then our rule would have been positive charges move opposite the field, negative charges move with it. We didn't go that route. We ended up saying, well, we'll call the field the direction the positive charge moves. And then the rule is that the negative charges just move opposite that. So this was kind of we had to because there's two different types of charge. Whereas for gravity, for instance, we don't have this issue. There's only one type of mass. And so it's very reasonable to automatically say the field is just the direction that mass gets pulled. There isn't a thing of, well, what if it's a negative mass? So fields sort of naturally have a direction for gravity. For electric fields, we have to pick. We have a convention for the direction. Is that getting a little better?
Yeah.
Okay. So if I come back to the question, in defining an electric field, a test charge is used. Is the test charge positively or negatively charged? Really, this is asking what historical convention did we pick? And we picked, see what the positive charge does. That's how we'll define the direction of our electric field. And so, because of that definition, the field vector is in the direction of the force on a positive charge. We didn't decide to use the force on a negative charge as our convention for the field direction. And we do have several unfortunate conventions like that. So by convention, what I mean is like for trigonometry, they just decided that clockwise is negative angles and counterclockwise is positive because there's no actual reason that has to be the case. But you do need to decide so that you can consistently define angles once you've done that. It's a similar issue here. There's no reason it had to be the positive charges that are what define the direction of the field, but we did have to pick something to define it. Okay, any other questions?
So back to the graded practice for chapter 23.
Yes.
The questions after the one that I said, questions 6 and 7, have like x equals 5r divided by 4, and I'm wondering, like, does that mean we have to like treat it as a slope and like move it 5x and then down 4? Like, I'm just confused on that.
No, it's saying like 5/4 of the radius, so 1.25 times the radius. So part 6. Yeah, no, it's just saying move it to x equals 5/4 of r or 1.25 r. So move it a full radius to the side and then a quarter of a radius past that.
Okay, and then what about for number 7? Because I know it has us move the y direction too.
So that's move it 3/4 of a radius and also up 3/4 of a radius.
Could you like show me like visually?
Yeah. So let me, moving it one full radius to the right would be that, right? Now I'm going to move it one additional quarter of a radius past that. So about there. And actually, I mean, it has a grid, so I could say the radius is 2 of these grid squares. So a quarter of a radius is a half of a grid square. So this would be about 5/4 r.
Okay, I can get it for a little bit.
It's just a very clunky way of them saying move this sphere until the charge is not inside of it. And then for 7, move the sphere so that we've got it a little bit over the right and a little bit up, but the charge will still be inside of it. Does that really change anything? And the answer is no. Look at that flux counter. Here's the easy way to answer this question is the flux will be that number when the charge is inside the sphere. The flux will be 0 the moment the charge is not inside the sphere. And it's because that's what Gauss's law says. The flux is equal to, or at least proportional to, how much charge is inside of your bag. If there's no charge in there, no flux. If there is charge in there, the flux is equal to the amount of charge divided by epsilon 0. It is clunky, and I can't edit it. If I could, I absolutely would. Because Wiley is terrible in a lot of things, but it is our only option, unfortunately. So this is at least an interactive thing to where you can sort of see it rather than just do yet another equation and see what happens. But I'm really imagining this as like, if I use that fire hydrant analogy, I've got a trash bag and I'm moving it around. And what I'm going to find is as long as the fire hydrant's inside of it, water is spraying out of the bag. The moment the bag is not enclosing the fire hydrant, water is not spraying out of it anymore, not spraying out of the bag anymore.
Yeah, I think what was confusing me was just like the way it was written, like how it says 3r before. I think it would have been better if it just said like 3/4r or something like that.
Yeah, I think there are a lot of things like that. And that's actually one that I can. So I'm not sure if it says it for students. Do y'all have a thing where you have report content error at the bottom? Anyway, if you do that to like give them feedback sometimes and say like, I don't like the way this is phrased. Is there a way we can just adjust the phrasing? And it's your right to do that just as much as mine. Like I'll put that in for this one, but I'm just saying like if you feel that the question itself is poorly worded, let them know because otherwise it just stays like that and it's worse for the next person. Yeah, if it were me writing this, I would probably say it as move the sphere up and to the right until the charge is no longer inside of it. What's the flux through it now? No other questions? If not, well, we can call it there. All right, well, y'all have a good weekend. So I won't see you till, no, I'll see you tomorrow. Have a good day.